Hey everyone, and welcome to another Deep Dive.
Yeah, it's great to be here.
Today we're going really deep,
Oh, yeah.
like to the center of the Earth deep.
Huh. Sounds intense.
It is. We're talking about Earth's interior,
A topic that's not only fascinating,
but also super important for understanding things like earthquakes,
volcanoes.
even how we find valuable resources like minerals.
Absolutely. It's all connected.
Oh, and before we get too deep into this,
Hey.
don't forget to hit that like button.
And subscribe to the channel.
It really helps us out,
And make sure you click that bell icon.
so you don't miss any future deep dives.
All right, let's get started.
So how do we actually know what's inside the Earth?
I mean, we can't just dig a hole to the core, right?
Well, there are a few ways.
Some direct evidence comes from things like volcanic eruptions.
Where molten rock from deep inside the Earth is brought to the surface.
Right. And deep drilling projects can also give us some samples.
But those only go so deep.
Exactly. That's where indirect methods come in.
Okay, so tell me more about those indirect methods.
One of the most important tools we have is seismic waves.
From earthquakes.
Yep. Earthquakes release energy in the form of waves that travel through the Earth.
And by studying how these waves travel,
Their speed, how they bend or reflect.
we can learn a lot about the different layers of the Earth. So it's like using sound waves to see inside the human body.
Exactly. It's like an ultrasound for the Earth.
That's so cool. But earthquakes aren't exactly predictable events.
True, but luckily they happen frequently enough
And scientists have developed really sophisticated instruments.
to record and analyze these seismic waves.
Okay, so seismic waves are one way to study Earth's interior.
What else?
Well, I've heard that meteorites can offer some clues
They can. Meteorites are basically space rocks.
that have landed on Earth.
And because they formed in the same solar system as Earth,
Studying their composition can give us insights into the building blocks of our own planet. So by looking at these space rocks,
we can get a better understanding of what's right under our feet.
it's like looking to our cosmic neighbors to learn about ourselves.
Exactly. It's all connected.
And we can't forget about gravity and Earth's magnetic field.
Those also provide clues about what's going on deep inside.
Right. Variations in these forces can tell us about the density
Composition.
and even the movement of materials within the Earth. It's like having a giant invisible hand giving us hints.
Exactly. It's all about piecing together the clues.
So we've talked about seismic waves, meteorites, gravity, and the magnetic field.
All tools for understanding Earth's interior.
But let's focus on those seismic waves for a bit.
There's a lot to unpack there.
I remember from school that there are different types of seismic waves.
You've got a good memory. There are body waves and surface waves.
Body waves, surface waves, what's the difference?
Body waves travel through the Earth's interior.
Like those X-rays we talked about.
Exactly. They give us information about the deep layers.
And there are two types of body waves, right?
Right. P waves and S waves?
P waves are the fast ones, right?
Yeah. Primary waves.
They can travel through both solids and liquids.
And they're the first to arrive at a seismic station after an earthquake.
Okay, so if P waves are the speedy messengers,
Then S waves are the ones that shake things up.
literally,
Literally. S waves or secondary waves are slower.
and they can only travel through solids.
This turned out to be a crucial clue for understanding the Earth's structure,
Why is that?
because scientists noticed that S waves were missing in certain areas.
What do you mean missing?
Like they just disappeared.
That's strange.
It was, and it led them to a groundbreaking realization
Which was?
that the Earth's outer core must be liquid.
Wait, so because S waves couldn't travel through a certain part of the Earth?
Scientists figured out that it must be liquid.
Because S waves can't travel through liquids.
Exactly. It was a huge discovery.
Wow, that's incredible.
So,
So we've got our body waves traveling deep inside the Earth.
giving us clues about the layers.
What about surface waves?
Surface waves are the ones that cause the most damage during earthquakes.
So those images we see of buildings collapsing and the ground shaking,
That's the work of surface waves.
they travel along the Earth's surface.
And they come in two main types: love waves and Rayleigh waves.
Love waves, rail waves,
Love waves move side to side.
and Rayleigh waves have a rolling motion.
Exactly. And both can cause a lot of destruction.
Okay, so we've got body waves diving deep,
And surface waves causing chaos up top.
but how do all these waves help us understand the structure of the Earth?
Well, remember how we talked about different materials affecting the speed of seismic waves?
Yeah, denser materials mean faster waves, right?
Exactly. And those waves can also be reflected or refracted?
Like bouncing off a mirror or bending as they pass through different mediums.
Precisely. By studying these patterns,
Scientists can map out the boundaries between the different layers of the Earth. It's like using sound to see the invisible.
it is. And this brings us to those shadow zones we mentioned earlier.
Shadow zones.
Those are areas on Earth's surface where certain seismic waves just don't arrive after an earthquake.
So like there's a dead zone where the waves are blocked.
Exactly. And the existence of these shadow zones.
Was it another key piece of evidence for the liquid outer core?
If it were solid, those waves would have passed through.
Okay, so it's all starting to come together.
Like a giant puzzle.
We've got our different types of seismic waves.
And their unique behaviors.
Now let's talk about the layers themselves.
The Earth isn't just one big ball of rock.
Oh, I know. There are layers, right?
You got it. And each layer has its own unique properties.
Like a delicious layer cake.
Haha. Well, sort of. Let's start with the crust. The outermost layer.
One we live on.
Exactly. It's surprisingly thin compared to the other layers.
It doesn't feel that thin when I walk on it.
I know, right? But on a planetary scale, it's like the skin of an apple.
And there are two types of crust. Oceanic and continental.
Oceanic crust is denser and made mostly of basalt.
And continental crust is less dense and made mostly of granite.
Hmm.
So the ocean floor is made of different stuff than the continents.
It is. And beneath the crust, we have the mantle.
The largest layer of the Earth.
Yep. It's sandwiched between the crust and the core.
And it's mostly solid rock, right?
It is, but it's not as simple as that.
Ooh, how so?
The mantle is so hot and under so much pressure.
That it actually flows very slowly over time. Wait, solid rock that flows. How is that possible?
It's mind-boggling, right? But the conditions deep inside the Earth are extreme.
And this slow movement of the mantle is what drives the movement of tectonic plates.
We'll talk more about that later.
Okay, I can't wait. So the mantle is this huge layer of mostly solid but slowly flowing rock.
And within the mantle, there are a few distinct zones.
Like what?
Well, the uppermost part of the mantle, along with the crust, forms a rigid layer called the lithosphere.
The lithosphere.
Yep, it's like a cracked eggshell floating on top of the asthenosphere.
The asthenosphere.
Right, that's a partially molten layer beneath the lithosphere.
So the lithosphere is rigid and the asthenosphere is gooey.
A good way to think about it. And both are part of the mantle.
Okay, I think I'm getting it. So we've got the crust and the mantle.
And now for the grand finale, the core.
The heart of the Earth.
Exactly. And it's divided into two parts, the outer core and the inner core.
Both made of iron and nickel-rite.
Got it. But they have very different properties.
Okay, tell me everything.
The outer core is liquid.
Liquid metal.
Liquid iron and nickel. And it's constantly churning.
It sounds like something out of a sci-fi movie.
It's pretty incredible. And this churning is what generates Earth's magnetic field.
So the magnetic field that makes our compasses work
And protects us from harmful radiation from the sun.
is created by a giant ball of liquid metal sloshing around deep inside the Earth.
It is. Pretty amazing.
That's
Yeah.
mind-blowing. Okay, what about the inner core?
The inner core is solid.
Solid, but it's even hotter than the outer core,
It is. But the pressure at the center of the Earth is so immense.
that it forces the iron and nickel atoms into a solid state. So it's like squeezing a snowball so hard that it turns into ice.
Even though it's still cold.
Wow. So to recap,
Let's do
we've got the crust, the thin rocky skin we live on,
the mantle. Mostly solid, but flows very slowly, divided into the rigid lithosphere and the gooey asthenosphere.
and the core, with its liquid outer part responsible for our magnetic field and its solid inner part.
All thanks to incredible pressure.
It's like a whole world within our world.
It is, and understanding the structure is crucial for understanding so many other Earth processes.
Okay, I'm ready for more.
Let's talk rocks.
Rocks, aren't they just boring lumps of matter?
Oh no, rocks are far from boring. They're a window into Earth's history.
And they hold clues about the processes that have shaped our planet.
You got it. And there are different types of rocks, each with its own story to tell.
I know there are, but I always get them mixed up.
No worries. Let's do a quick Geology 101.
Perfect. Start with the basics.
We can broadly classify rocks into three main types: igneous, sedimentary, and metamorphic.
Igneous, sedimentary, metamorphic. Okay, go on.
Igneous rocks are formed from the cooling and solidification of molten rock.
So like when lava from a volcano cools and hardens?
Exactly. That's an example of an extrusive igneous rock because it formed at the surface.
Extrusive. Okay. What about igneous rocks that form underground?
Those are called intrusive igneous rocks, like granite.
Granite, like my kitchen countertop.
Yep. It formed from magma that cooled slowly beneath the surface.
And that's why it has those big crystals.
Exactly. The slower the cooling, the larger the crystals.
So it's like slow cooking versus flash frying.
I like that analogy. Okay, now let's talk about sedimentary rocks.
Those are the ones that form in layers, right?
You got it. Sedimentary rocks are formed from the accumulation and cementation of sediments.
Sediments like sand and mud.
Exactly. Over time, these sediments are deposited in layers, often at the bottom of oceans or lakes.
And then they get compacted and cemented together to form solid rock.
It's like nature's way of recycling old rocks into new ones.
So those layers are like chapters in Earth's history book.
They are. And sometimes they contain fossils.
Fossils. Like dinosaur bones?
Dinosaur bones, shells, ancient plants.
So those fossils give us a glimpse into ancient ecosystems.
They do. It's like traveling back in time.
This is getting me excited about geology. What about metamorphic rocks?
Metamorphic rocks are all about transformation.
Transformation.
They form when existing rocks, either igneous or sedimentary, are changed by heat, pressure, or both.
So they're like the remade versions of other rocks.
Exactly. Think of it like baking a cake.
Baking a cake.
The ingredients are like the original rock.
And the heat and pressure of the oven are like the forces that transform them.
Exactly. For example, marble, which is often used in sculptures and buildings,
Is a metamorphic rock formed from limestone.
and slate, which is used for roofing and flooring.
You're formed from shale. Okay, so igneous rocks come from molten rock.
Sedimentary rocks are made from layers of sediment.
And metamorphic rocks are transformed from existing rocks.
You got it. And this whole process of rocks changing from one type to another is called the rock cycle.
The rock cycle.
It's a continuous process driven by Earth's internal and external forces.
So rocks are constantly being created, destroyed, and transformed.
It's a beautiful illustration of how dynamic our planet truly is.
It really is. And speaking of dynamic processes,
Let's talk about plate tectonics.
oh yeah, plate tectonics. The idea that Earth's surface is broken into these giant plates.
That are constantly moving around.
It's like a giant jigsaw puzzle where the
Yeah.
pieces are always shifting.
A very slow-moving jigsaw puzzle.
And this movement is driven by those convection currents in the mantle, right?
You got it. Hot material rises, cools, and sinks, creating a continuous cycle of motion.
So those convection currents are like giant conveyor belts, dragging the plates along with them.
Exactly. And the way these plates interact at their boundaries.
Creates all those amazing features on Earth's surface.
Mountains, oceans, earthquakes.
It's all connected. But before we dive into those plate boundaries,
Which we will in the next part of our deep dive.
don't forget to like and subscribe.
And click that bell icon.
See you next time.
Bye for now. Welcome back, everyone.
It's great to be back underground.
Hey, yeah, we're still in our deep dive.
Into the fascinating world of Earth's interior.
Last time we talked about those tectonic plates.
Those giant pieces of Earth's crust that are constantly moving around.
And how those movements can cause earthquakes and volcanoes.
It's incredible to think about those forces shaping our planet.
It really is. But how do those plate movements actually create the landscapes we see?
Yeah, like how do we go from shifting plates to towering mountains?
Or vast canyons and deep ocean trenches?
That's where we're going to explore today.
We're diving into the world of geomorphology.
Geomorphology.
It's basically the study of landforms and the processes that shape them.
So like how mountains and valleys are formed.
Exactly. And how those features are constantly changing.
Due to erosion, weathering, and all those other forces.
Right. It's a dynamic process, always happening.
It sounds complicated.
It can be, but we'll break it down into manageable chunks.
Great. I'm ready to learn.
Okay, let's start with a key concept. Denudation.
Denudation. That sounds intense.
It might sound like a big word,
It does.
but it basically means the wearing down and breaking up of Earth's surface.
So like erosion.
Erosion is part of it, but denudation is a broader term.
Okay, so what else is involved?
Denudation includes weathering.
Weathering. Right. That's when rocks are broken down into smaller pieces.
Exactly. And there are two main types of weathering, physical and chemical.
Physical weathering, I can imagine that.
Like rocks being smashed by waves.
Or freezing and thawing.
Yep. When water seeps into cracks in a rock and then freezes, it expands and can break the rock apart.
So it's like nature's frost wedging.
It is. Pretty powerful, right?
What about chemical weathering?
Chemical weathering involves chemical reactions that break down the rock.
Like acid rain dissolving limestone.
Exactly. Acid rain can create caves and sinkholes.
Wow, so even rain can be a force of nature.
It is. And once those rocks are broken down by weathering,
Then erosion can carry those pieces away.
you got it. Erosion is the transport of weathered material.
And that can happen through wind, water, or ice.
Right. Think of a rushing river carrying away sediment.
Or wind blowing sand across a desert.
And glaciers, those massive rivers of ice, can carve out entire valleys.
So weathering breaks it down, and erosion carries it away.
It's a powerful duo. But what happens to all that material that's eroded?
Yeah, where does it all go?
It eventually gets deposited somewhere else.
Like at the bottom of the ocean or in a river delta?
Exactly. And over time, those loose sediments can be transformed back into solid rock.
Wait, so those tiny pieces of sand and mud can become rocks again?
They can. That process is called lithification.
Lithification. Okay, how does that work?
It involves compaction and cementation.
Compaction is like squeezing the water out of the sediments, right?
Exactly. And cementation is when dissolved minerals in the water precipitate out and bind the grains together.
So those loose sediments are like ingredients.
And compaction and cementation are the processes that bake them into a solid rock cake.
Uh-huh. I like that analogy. It's like a giant recycling system.
Breaking down rocks in one place and building them up in another.
And that's all part of the rock cycle we talked about before.
It all comes full circle. It's amazing how interconnected everything is.
It really is. So we've talked about denudation, weathering, erosion, and lithification.
All those processes that shape Earth's surface.
But what about minerals?
Ah, minerals. Those fascinating building blocks of rocks.
Right. They're not just pretty to look at, they're essential components of rocks.
They are. And they play a huge role in shaping the landscape.
So can we geek out about minerals for a bit?
Of course. What do you want to know?
Well, first of all, what exactly are minerals?
A mineral is a naturally occurring inorganic solid with a specific chemical composition and a defined crystal structure.
Okay, so they're not just random chunks of stuff.
Nope. They have a very specific makeup.
Like a recipe with precise ingredients.
Exactly. For example, quartz is a mineral made of silicon and oxygen atoms arranged in a specific way.
And that specific arrangement is what gives it its hardness and transparency.
Precisely. Different minerals have different properties based on their chemical composition and crystal structure.
So how do minerals form?
Most minerals form from the cooling and crystallization of molten rock.
Like when magma or lava cools down?
Yep. As the molten rock cools, different minerals crystallize out at different temperatures.
So it's like a giant underground chemistry experiment.
It is. And minerals can also form through precipitation from water.
Precipitation, like rain.
Not just rain, but also groundwater and even seawater.
Okay, so minerals can come from molten rock or water.
And some minerals even form through biological processes.
Biological processes, like from living things.
Yep. For example, the shells of marine organisms are made of calcium carbonate.
Which is a mineral.
Exactly. So minerals can form in all sorts of ways.
It's amazing how diverse they are. But why are minerals so important to us humans?
Well, for one thing, they're the building blocks of rocks, so understanding minerals helps us understand Earth's history and processes.
Right, it's like learning the alphabet before you can read a book.
Exactly. And many minerals are economically valuable.
Like we extract metals from minerals, right?
Yep. Iron, copper, gold, all those come from minerals.
And we use minerals in construction, manufacturing, technology.
Even our food relies on minerals in the soil.
So minerals are literally the foundation of our civilization.
They are. And they can also tell us a lot about the geological history of an area.
How so?
Well, the type of minerals present can indicate the temperature and pressure conditions that existed when those minerals formed.
So they're like tiny time capsules.
Exactly. Preserving clues about Earth's past.
Okay, I'm officially a mineral enthusiast now.
Yeah.
There's so much more than just pretty rocks.
I'm glad to hear it. They're essential to our planet and our lives.
So we've explored the amazing world of minerals.
Those building blocks of rocks.
Now let's get back to the rocks themselves.
We talked about the three main types: igneous, sedimentary, and metamorphic.
But can we dive a little deeper into their specific characteristics?
Of course. Let's start with igneous rocks.
Those are the ones formed from molten rock.
Right, and we can classify them based on their texture and composition.
Texture, like how rough or smooth they feel.
Not exactly. In geology, texture refers to the size, shape, and arrangement of the mineral grains in the rock.
Okay, so what determines the texture of an igneous rock?
The cooling rate of the molten rock.
So if it cools slowly,
It'll have a coarse-grained texture with large crystals like granite.
and if it cools quickly.
It'll have a fine-grained texture with small crystals like basalt.
So it's all about how much time the minerals have to grow.
Exactly. And composition refers to the types and proportions of minerals present in the rock.
So like a granite might be rich in quartz and feldspar,
While a basalt might be rich in pyroxene and olivine.
and each mineral has its own unique properties,
So the composition of a rock influences its overall characteristics.
like its color, hardness, and density.
Got it. Texture and composition are like the ID cards of igneous rocks.
Okay, what about sedimentary rocks?
Sedimentary rocks are all about layering or stratification,
Right. Those layers are formed from the accumulation of sediments.
and each layer represents a different episode of deposition.
So the sequence of layers can tell us a lot about the environment at that time.
Exactly. Like a layer of sandstone might indicate a beach environment,
And a layer of shale might indicate a deeper water environment.
and those layers often contain fossils which add even more detail to the story.
So sedimentary rocks are like time capsules, preserving snapshots of Earth's history.
They are, and they're also important for understanding the formation of oil and gas deposits.
Really? How so?
Well, oil and gas often form in sedimentary basins where organic matter is buried and transformed over millions of years.
So the layers of sediment are like a giant pressure cooker, slowly cooking up those fossil fuels.
That's a good way to think about it. Okay, let's move on to metamorphic rocks.
Those are the ones that have been transformed, right?
Exactly. They form when existing rocks are subjected to heat, pressure, or both.
And this can change the texture and mineral composition of the rock.
Right. For example, limestone, a sedimentary rock, can be transformed into marble, a metamorphic rock.
Marble, like those beautiful scat gems.
Yep. And shale, another sedimentary rock, can be transformed into slate.
Slate, like those roof tiles.
Exactly. And one of the key characteristics of metamorphic rocks is foliation.
Foliase.
It's a layering or banding in the rock caused by the alignment of minerals under pressure.
So it's like squeezing a stack of papers.
The papers align themselves in the direction of the pressure,
And in metamorphic rocks, this creates those beautiful patterns and textures.
like the swirling patterns in gneiss or the fine layering in slate.
So foliation is a sign that the rock has been through some serious pressure.
It is. It's evidence of the powerful forces that operate deep inside the earth.
Wow, we've covered a lot of ground today.
We have, from denudation to minerals to the different types of rocks.
And how those rocks are constantly being formed, transformed, and recycled.
It's all part of the amazing story of Earth's ever-changing landscape.
It really makes you appreciate the dynamic nature of our planet.
It does. And it all ties back to that grand unifying theory of plate tectonics.
Which we'll explore in more detail in the next part of our deep dive.
So stay tuned for more geological adventures.
And don't forget to like and subscribe.
And hit that bell icon so you don't miss out.
All right, welcome back to the final part of our deep dive into Earth's interior and geomorphology.
I'm excited to wrap up this epic journey.
Thank you. We've covered so much ground already, from the core to the crust, from rocks to minerals.
We've seen how those massive tectonic plates shape the world around us.
It's mind-blowing to think about those forces at work.
It really is. But before we wrap up, I want to make sure we connect all the dots.
Yeah, let's tie it all together.
Okay, so we talked about how divergent boundaries create new crusts.
Those cracks in the Earth's surface where magma rises up.
But how does that lead to the formation of entire oceans?
I was wondering that myself.
Oh, imagine those divergent boundaries constantly pulling apart.
Like a giant zipper unzipping,
And as they pull apart, magma fills the gap.
creating new oceanic crust.
And over millions of years, this process can create those vast ocean basins we see today.
So the Atlantic Ocean, for example, is basically a giant rift valley.
That's been filling with water for millions of years,
It's incredible to think about those plates slowly drifting apart.
creating space for an entire ocean to form.
And the Atlantic is still growing wider today, right?
It is. Those plates are still moving apart, even now.
That's wild. Okay, so divergent boundaries create ocean basins.
What about convergent boundaries?
Those are the ones where plates collide.
And they're responsible for those deep ocean trenches.
Those underwater canyons that are deeper than Mount Everest is tall.
Exactly. And they form when one plate is forced beneath another.
And that process called subduction.
Right. The denser plate usually dives down beneath the less dense plate,
And that creates a deep depression in the ocean floor.
the trench. And as that subducting plate sinks into the mantle,
It can trigger earthquakes and volcanoes.
you got it. So convergent boundaries are responsible for both those dramatic trenches.
And those fiery volcanoes.
It's like a constant battle between creation and destruction.
And it's all driven by those powerful tectonic forces.
Forces that have shaped our planet for billions of years.
But it's not just about the physical landscape.
Those features also have a major impact on life on Earth.
Oh yeah. How so?
Well, those deep ocean trenches, as dark and inhospitable as they may seem.
They're actually teeming with life.
We're talking strange and wonderful creatures that have adapted to those extreme conditions.
So there are entire ecosystems that exist in those trenches.
It's one of the most amazing examples of life's resilience.
Life finds a way.
It does. And those volcanoes formed at convergent boundaries.
They can be both destructive and creative.
In the short term, volcanic eruptions can be devastating.
But they also release nutrients into the soil, making it fertile.
And over millions of years, volcanic activity can create new islands and even entire mountain ranges.
It's a powerful reminder that even the most destructive events can eventually lead to new life.
A cycle of renewal and rebirth.
Okay, we've explored the depths of the oceans, the heights of mountains.
Now let's bring it back down to Earth.
Literally. Let's talk about the processes that shape the land we live on.
The soil, the hills, the valleys.
All that good stuff.
That's where we get into erosion and weathering.
Those forces that are constantly sculpting and reshaping Earth's surface.
Like nature's artists, always at work.
I remember learning about erosion in school.
It's basically the transport of weathered rock and soil
And weathering is the breakdown of those materials.
through contact with the Earth's atmosphere, water, and living things.
So weathering breaks it down, and erosion carries it away.
A dynamic duo. And water is one of the most powerful forces of erosion.
Yeah, rivers can carve canyons.
And ocean waves can erode coastlines, creating those dramatic cliffs and arches.
It's incredible how much power water has,
It is. But wind can also be a major force of erosion,
especially in deserts.
where there's not much vegetation to hold the soil in place.
Wind can create those giant sand dunes.
And sculpt those strange and beautiful rock formations.
It's like a natural sandblasting process.
And an ice, in the form of glaciers, is another powerful erosional force.
Glaciers are like giant bulldozers, slowly carving out valleys.
And transporting huge boulders over long distances,
They've shaped many of the landscapes we see today.
especially in places like Norway and the Great Lakes region,
It's amazing to think about all these forces at work.
constantly shaping and reshaping our planet,
It's a never-ending process.
driven by the internal and external forces of the Earth.
And it's not just about the physical landscape.
Erosion and weathering also play a key role in soil formation,
That's right. The soil that supports all plant life.
the foundation of agriculture and ecosystems.
It's all connected.
It is. Every part of this system is intertwined.
Well, this has been an incredible journey.
From the depths of the Earth to the surface and beyond,
We've explored the hidden layers, the dynamic processes.
and the amazing features that make our planet so unique.
I feel like I have a whole new understanding of how the Earth works.
I'm glad to hear it. It's a fascinating subject, and there's always more to learn.
Absolutely. And I hope our listeners have enjoyed this deep dive as much as we have,
If you've learned something new today,
or just been inspired by the wonders of our planet.
don't forget to like and subscribe to our channel.
And hit that notification bell so you don't miss out on any future explorations.
Thanks for joining us on this incredible journey.
Until next time, keep exploring.